We have studied what is absorption spectra and what is emission spectra. We have seen that in the absorption spectra, there were some dark lines. These dark lines correspond to the wavelengths that were absorbed by the sample. So, these lines are missing. That's why dark lines are observed. And in the emission spectra of the same sample, it will be observed that bright lines are observed at the same positions where the dark lines were observed in the absorption spectra, which means the wavelengths that were absorbed by the sample and the sample gets excited. So, when it will return to the ground state or the lowest energy level, then they will emit the same radiations, that is radiations of the same wavelength. Therefore, absorption spectra is kind of a photographic negative of the emission spectra. Now, since in these spectra lines were observed, so they are also called line spectra. Since absorption spectra and emission spectra are obtained in the form of lines, they are called line spectra. Now, one example of line spectra was the hydrogen spectrum, and the study of spectra is called spectroscopy. Okay. So, study of absorption spectra will be called absorption spectroscopy, and study of emission spectra will be called emission spectroscopy. So, one example was line spectrum of hydrogen. Okay. When an electrical discharge is passed through a hydrogen molecule, it dissociates. Hydrogen molecule will dissociate into two hydrogen atoms. Okay. And when these hydrogen atoms are energetically excited, they emit electromagnetic radiations of discrete energies. Or discrete frequencies. Okay. Now, since they emit discrete energies, so let's say we have E1, E2, E3. So, E1 is equal to H nu 1, E2 is H nu 2, E3 is H nu 3. Similarly, E1 can be written as Hc by lambda 1, E2 equal to Hc by lambda 2, E3 equal to Hc by lambda 3. So, for different values of energy, we will have different values of wavelength and frequency. So E1 will correspond to nu 1 and lambda 1, E2 will correspond to nu 2 and lambda 2, E3 will correspond to nu 3 and lambda 3. So due to different wavelengths or frequencies, we obtain different spectral lines. Okay, so hydrogen spectrum consists of several spectral lines. Okay. Now there was one expression for these spectral lines. How can these spectral lines be expressed mathematically? Spectral lines can be expressed in terms of wave number. In terms of wave number, that is nu bar. So the formula was nu bar equal to 109677 into 1 by n1 square minus 1 by n2 square, and the unit will be centimeter inverse. So in this case, this number is called the Rydberg constant. And these n1 and n2, all these can be any integer value. What are these integer values? They are different levels. Different levels of energies. Okay. N1 can have any integer value like 1, 2, 3, 4 and so on. Now N2 will be greater than N1. That is, let's say if the hydrogen atom is absorbing energy, it will be excited to a higher energy level, and then when it comes from the higher energy level to the lower energy level, it will emit energy. So N2 should be greater than N1. So if N1 is 1, 2, 3 etc., what will be the value of N2? N2 will also have integer value. It can be written as N1 plus 1, N1 plus 2, N1 plus 3 and so on. Okay. Now all the spectral lines of hydrogen atom had some names. So now we will discuss the names. So for the first one, let's say for N1 equal to 1. So if N1 is 1, then what will be the first excited state? Actually, lowest energy state is called the ground state. Okay, and the energy which is just above the lowest energy state, like these are the energy levels. Okay, if this is the ground state, then we will call this excited state, fast excited state. This will be second excited state, and so on. So if we consider the ground state as N1, then the first excited state will be N1 plus 1, that is N2 suppose. Okay, and the second excited state will be N1 plus 2 and so on. So when we are talking about the names of spectral lines of hydrogen, we are talking about the first excited states. Okay, so for N1 equal to 1, so what will be N2? N2 will be N1 plus 1, that is the first excited state will be 2. The second excited state will be 3. Then 4. It can happen like this. So for one ground state, we get a series of spectral lines. We get a series of spectral lines. When N1 equal to 1 and excited state can be 2, 3, 4 and so on, we call this the Lyman series. For N1 equal to 1, we get the Lyman series. Lyman series has a spectral region in UV or ultraviolet. So the Lyman spectral lines fall in the UV region, that is their wavelength and frequency matches the UV region. Now number 2, when N1 equal to 2, if N1 equal to 2, then what will be the value of N2? N2 can be 3, 4, 5 and so on. These series of lines are called the Balmer series. Balmer series comes in the visible region. Balmer series is the only spectral series of hydrogen atom which comes in the visible region. Now let's consider when N1 equal to 3. Then what will be the value of N2? N2 can be 4, 5, 6 and so on. We call this one as the Paschen series. And the spectral region will be infrared or IR. The fourth one, when N1 equal to 4, then N2 can be 5, 6, 7 and so on. We call this the bracket series. Here also the spectral region is IR. And the fifth one, when N1 equal to 5, then N2 will be 6, 7, 8 and so on. We will call this as the fund series, but it starts with a P, remember. Fund series, and here also the spectral region is IR. So what we got? Lyman, Bummer, Paston, Bracket and Fund. So Lyman when n1 equal to 1 and n2 will be naturally 2, 3, 4 and so on, and this is UV. Bummer corresponds to n1 equal to 2, it falls in the visible region. Paston has n1 equal to 3, it falls in IR. Bracket has n1 equal to 4, it falls in IR. Fund has n1 equal to 5 and this also falls in IR. Now, if we express these lines in the form of a diagram, how can we say? Suppose this is the line of n equal to 1. This is n equal to 2, 3, 4, 5, 6, 7, 8, 9, and suppose it goes up to infinite. Then we can draw the spectral lines in these diagrams and we can see how the series of the lines are divided. Next we will study about the spectral lines. Thank you.